Okay, think back. Maybe when you were a kid. Science class, or just, playing around. Do you remember messing with magnets? That, like, sheer wonder, holding one and watching a paperclip just jump to it without you even touching it, or maybe sprinkling iron filings, seeing them just magically arrange themselves into those really cool patterns. It was just pure awe, wasn't it? How could something totally invisible push and pull things so strongly? All right, let's unpack this a bit. Today, we're doing a deep dive into that whole mysterious invisible world. Magnetism. Our goal is really to make sense of it, clarify the basics so it clicks for you. Moving from that kid-like wonder to really understanding how it shapes things.
Exactly. Yeah, our mission here is to explore those core ideas, what magnetism is, how it actually works, and maybe most importantly, why it matters so much in our everyday lives.
Yeah.
We're going to sort of build it up step by step, make sure you get a good handle on these concepts. We'll start with, what magnets and magnetic force actually are, then look at the poles, that N and S thing. After that, we'll talk about visualizing the force with magnetic fields, the rules for how magnets interact, and then, yeah, connect it all to Earth itself, our planet.
It really is amazing, though, how a force can just act across empty space. Pushing, pulling, no strings attached. Literally, you could hold a magnet like inches away and zip. That paperclip just flies right over. It felt like magic.
And honestly, even knowing the science now, it still feels kind of wondrous, that basic interaction. It's true, yeah. That raw pull or push, it never really loses its cool factor. So let's get down to it. What is a magnet, fundamentally? Well, at its simplest, a magnet is just any material, any substance that can attract certain metals like iron, nickel, cobalt, those paper clips, steel balls, even how your fridge door kind of seals itself shut. That's magnetism. Now, the strength of that polar push, that invisible energy, that's what we call magnetic force. It's the effect you feel, even though you can't see the mechanism. And what's really fascinating deep down is it all comes from moving electric charges, like at the atomic level, mostly the spin and orbit of electrons inside the material. That's what creates these tiny magnetic moments. And when they line up, boom, you get a magnet. Okay, so magnets attract stuff. They exert this invisible force, and it comes from electrons doing their thing. But here's where it gets really interesting and kind of unique, right? Compared to, say, electricity. Magnets always have two distinct spots. Poles, you've heard of them, North Pole, South Pole, N and S, just part of being a magnet, every single one, no matter the size or shape. And that brings us to something really crucial, maybe even a bit mind-bending about magnetism. A magnet cannot exist with just one pole. It's impossible. You can't have like an isolated North Pole floating around by itself, or just a South Pole, what scientists call a magnetic monopole. We just don't see them in our everyday world. Think about it. If you take a bar magnet, right?
Yeah.
And you snap it in half.
Yeah. What happens?
You don't get one piece that's just north and one that's just south. Nope. Instantly, each of those new, smaller pieces will still have both the North Pole and a South Pole.
Wow, really?
Yeah, it's like magnetism insists on this pairing.
Yeah.
Always together, no matter how small you break it. It really shows how fundamental this duality is. Very different from electric charges, where you absolutely can have just a positive charge or just a negative charge on its own.
That is fascinating. Okay, so if this force is invisible, always pushing and pulling, and the poles can't be split up, how do we even picture it? How do we understand the space where this force is active? It feels hard to grasp something you can't see.
Right, and that's where the idea of a magnetic field is so useful. It's a brilliant concept. A magnetic field is basically just the area around a magnet where its magnetic force can be felt, where it has influence. It's that invisible bubble of push and pull. And to help us visualize it, we use these things called magnetic field lines. They're imaginary lines, of course, but we draw them to show the direction and the strength of the force in that field. Usually we draw them coming out of the North Pole,
Okay.
looping around and going into the South Pole, forming these continuous closed loops. But here's the really cool part. These lines aren't just random squiggles. Their pattern, and especially their density, how close together they are, tells you something important.
Density, like how packed they are.
Exactly. The density of the lines shows the strength of the magnetic field right there. So if you see lots of lines packed tightly together, that means the magnetic field is strong in that spot.
Okay.
And where the lines are spread further apart, the field is weaker. It's a way for us to map out and actually, measure and understand these invisible forces. Super important for designing things like motors or hard drives.
Okay, so we've got these invisible fields mapped by lines showing pushes and pulls, which brings us right back to that classic thing. What happens when you bring two magnets close together? Anyone who's played with them knows Sometimes they snap together, sometimes they push apart really hard.
Mm.
There are definitely rules, right?
Oh, absolutely. Very simple, very fundamental rules.
Yeah.
And they're always the same. When you bring two magnets near each other, you get one of two main things happening. First, if you bring two, like, poles together, so north to north or south to south,
Yeah.
they repel, they push each other away. You feel that definite force trying to separate them, like trying to squish the same ends of two springs together. They just resist.
I know that feeling.
Second, the opposite.
Yeah.
If you bring two opposite poles together, a north pole facing a south
they'll
pole,
attract.
exactly, they attract. That's when you feel that pull and snap, they stick together. Those two simple rules, like poles repel, opposite poles attract, that's the basis for pretty much all magnetic interaction. It's what makes maglev trains float, using magnetic fields to lift and push them, or how electric motors work, turning electricity into motion, just using these pushes and pulls.
That snap, that attraction always felt like pure magic when I was a kid.
Definitely.
But speaking of size, we've been talking about, handheld magnets mostly, small stuff. Turns out, though, we're actually living on a giant magnet, which is, well, it's pretty mind-boggling when you stop and think about it.
It absolutely is. Yeah, the Earth itself acts like a huge, powerful magnet. It has this massive magnetic field. It stretches way out into space. We call it the magnetosphere. And this isn't just some interesting fact. It's incredibly important for life here. The most obvious example,
A compass.
right, the compass. A compass needle is just a tiny magnet, balanced really carefully. And because the Earth is this giant magnet, its field wraps around the whole planet. So that little compass needle naturally lines itself up with Earth's big magnetic field. And here's the slightly confusing bit, but it makes sense. The north pole of the compass needle actually points towards Earth's geographic north pole.
Okay.
But magnetically speaking, the pole up there near the geographic north pole is actually a magnetic south pole because opposites attract, remember?
Oh, got it. Okay.
Yeah, the south pole of the needle points towards the geographic south pole, which is near Earth's magnetic north pole. This whole setup, Earth being a magnet, is what guided sailors and explorers for centuries. And it also acts like a shield, protecting us from harmful stuff from the sun, solar wind, cosmic rays. It deflects a lot of it away, which is pretty vital. It does make you wonder, though, how does something like the Earth's core, all that molten metal swirling around, generate and keep this massive invisible shield going for billions of years?
So let's wrap this up for you. We've gone from that, like childhood amazement with magnets, to getting a handle on what they actually are, how their poles are inseparable, visualizing those invisible fields with lines, and even seeing how our whole planet is basically a giant magnet that guides and protects us. You've just taken a pretty deep dive into some really fundamental physics, unpacking how something unseen has such a huge practical impact.
Exactly. And understanding these basics, these principles of magnetism is really crucial because these forces are working everywhere in so many technologies, so many natural things around us, often without us even noticing. Think about the speakers you're hearing this through right now, or the hard drive storing your photos, medical stuff like MRI scans, super fast maglev trains. And yeah, Earth's shield against the sun, magnetism is it's this silent, powerful, totally essential force in our tech world and in nature too. So considering how much we can figure out just by looking closely at a simple magnet, what other invisible forces or basic concepts out there in your daily life are you curious about now? And, how might understanding those things maybe unlock some completely new ways of seeing the world for you?